So welcome back to the video, and we're going to continue from where we have left off. So in our event graph for BP Tetris, I'm going to delete all these nodes that we have created in the previous part. I only made it to show you what we have done in here, but now we're going to create a more advanced version of this. So I'm going to delete this off. So I have already created the nodes needed to do that. Once again, pause the video and recreate it in your project. It's all largely the same thing as what we have done in the previous video, except this time we have a different variable to store the x and y values in our for loops, and we're storing the reference of the plane that we have gotten from the screen array into a variable called bpPlaneRef, and we're storing the values we have gotten from both of these into this function called selectColor. Also, all these nodes are connected to the event node over here. And we have done this because we want our screen array to keep updating what to render as we play our game. I will go into more detail about this later on. So back to our selectColor function over here. You can add input pins into a function by selecting a function and navigating to details, inputs, and add the inputs in just like you would with adding variables. And inside our function, we are storing the reference of our BP plane into a local variable, and we're using the index that we have received from the Playfield into the switch on int variable over here. Now, before we continue, I need to quickly explain what kind of integer values we store in our Playfield. So like I have explained in the previous video, we're using numbers stored in our Playfield array to represent different elements or things in our game, like our borders, the empty spaces, and so on. And we're only using integer values from 0 to 9 because that's all we need for our game. And then based on the value of the element in our Playfield array, we are executing these nodes over here. And I'm using the same set of nodes we have used in the previous video to give colors to our planes in our screen array. I have also highlighted the nodes with comments to better explain what they are. And in case you don't know, you can add a comment to a bunch of nodes by selecting the nodes you want to comment and press the C key in your keyboard. You also have a bunch of settings over here to further control how you want your comments to appear like. So if the value of the element in our Playfield or the p-index is 0, then it's going to execute this node over here, and 0 means empty space, so we're going to give it a unique color. Likewise, if the value of the p-index is 9, it means that it's a border. So we're going to give it another unique color over here, and if the value of p-index is 8, we're going to execute this node over here, and the number 8 means that there is a line over there, and a line means that we got a row or multiple rows filled with Tetromino pieces. And instead of just instantly deleting the Tetromino piece in that row, we're going to set that particular row of Tetromino pieces a unique color for 1 second and then delete it. And then the numbers 1 to 7 each represent a unique Tetromino piece, and each of them are given a unique color to better differentiate them. So we're going to compile our blueprint and we're going to run our game. You can see everything's working fine. Our borders and our empty spaces are highlighted with a different color, and I'm going to get rid of these numbers over here. Alright, so I have gotten rid of the numbers on our planes. So now our game looks a lot more cleaner and nicer. And also I forgot to mention this, while giving colors to the Tetromino pieces, make sure to give bright saturated colors to our Tetromino pieces to better highlight them from the border and the empty spaces, and to better differentiate them from the other Tetromino pieces. So once we are all done with that, I'm going to go back to our event graph, and I have created a new string array called Tetromino that stores the information needed to spawn our Tetromino pieces, which are the pieces we can control and move around when the game is running. And inside our array, you can see we have 7 strings over here, and each string contains 16 characters that are stored in a combination of X's and dots. I'll go into more detail on how we are going to use this to create our Tetromino pieces later on. I will also be adding these strings in the description or the comments of this video, so you can just copy and paste them into your Tetromino array. So back over here, from the completed pin of our for loop in the x-axis, I have created these 2 for loops over here, And this time we're going to use them to display our Tetromino pieces. And after that, we have the nodes for getting a string at this specific index over here from our Tetromino array. And we are then converting that string into an array of characters using this node over here. This allows us to compare each characters inside our string to see if it matches with the character we are looking for. In this case, we are looking for the character X using the equal exactly string node. So it's this node over here under the string section over here, and we are reading the characters in such a way that they make up a 4x4 grid. This group of nodes should look familiar to you from our previous part. So if a character in our string matches with the one over here that we are looking for, then we are going to display that into our screen array using the same formula we have used before, except for this part over here, and have done this to display our piece at the center of our screen in the x-axis. So I'm going to run this project so you can actually see how all of this works. And while you're creating the nodes, make sure to set the p index as something like 1. So compile this project and run it. And you can see at the top of our game level, we have our Tetromino piece. So to explain how all of this works, I'm going to go back to our Tetromino array over here. And since I'm getting the string whose index is 3, I'm going to copy this string over here, which is at index 3, and paste it into my notepad over here. Now I'm going to zoom in a bit over here. I'm going to reformat this into a 4x4 grid. And when I do that, you can kind of see a silhouette of our Tetromino piece. Each of the X's you see in here represents the part that makes up our piece, and the dot represents empty space. To make it even more clearer, I'm going to add spaces in between the characters. And now we can more clearly see the shape of our Tetromino piece over here. And if I were to reformat each of the strings in our Tetromino array the same way, you can see they all represent different Tetromino pieces. This is what we have done in here with our nodes. We basically get the string that represents the piece we want to display and get the characters in such a way that they make up a 4x4 grid. And then we compare those characters to see if it is an X or not, and if it is, we display that in our screen array. And you can choose which piece you want to spawn by changing this value over here. So if I were to give a value of something like 0 and maybe change the value over here to something like 1, you can see we have a different piece now. Now we need to add the logic needed to move our pieces while our game is running. So back in our event graph, I have created some variables called current y and current x. These variables represent the location of our Tetromino piece in the x and y axis, and by default they are both set to 0. I have also commented out all the nodes for easier readability, so you can pause the video if you want to recreate them. So in our for loop for displaying or rendering our Tetromino pieces, I have done some modifications to our nodes that will allow us to change the location of our Tetromino piece as our game is running. I have also created a couple of keyboard event nodes over here. These nodes are used to check if a specific key is pressed or not, and if it is going to execute everything connected to the pressed execution pin over here. So after you're done recreating these nodes, we are going to run this project, and you can see I can actually move my Tetromino piece when I press the A or D key. So to understand how we are moving the pieces, we need to understand where the center or origin of our pieces are, because our pieces are generated column by column from the center or origin of our piece, just like our screen or Playfield array. To better demonstrate this, I'm going to run the game, and I'm going to click on this icon over here to detach from the player controller. And now I'm going to click on this plane over here, and this plane is the origin or center of our screen, because if I were to search for BP Tetris over here in our outliner, you can see it's located right over here in the same location as our first BP plane. So all the other planes are generated from this plane onwards. So if I were to change the location of this BP Tetris and then run the game again, you can see our first BP plane is generated from that location onwards. So I have taken this image from our game and I have made the dots in our Tetromino piece visible to better illustrate how the center of our piece is actually this cell over here. And if I were to go back to my notepad, you can see all of our Tetromino pieces have a dot at this cell over here. So if I were to modify this Tetromino piece in such a way that the X now appears at this cell over here at the origin of our piece, and then we are going to reconstruct this. So I have gotten a new combination of X's and dots that I'm going to now use to replace this piece over here, which is at index 0. And if I were to run this game, you can see the position of our piece is now different from where it once was. So back in our event graph, when we are changing the current Y and the current X variables over here, we are actually only changing the location of the origin of our piece. This is also one of the reasons why I have subtracted 2 from the result of these two nodes over here, otherwise it wouldn't exactly be in the middle. Now to rotate our pieces, we need a variable to store the current rotation and another keyboard event node to trigger the rotation when the key is pressed. I have also created a new function called rotate, and inside this function, I'm using these two local variables over here to store the X and Y values. I'm also using a modulo node over here, which divides the current rotation with the value 4, and the remainder of that division will be used to decide which of these nodes should we execute. Each of these 4 execution pins basically calculates what our rotated piece would look like and send the result to the return node over here. You can create a return node by adding a new variable in the output section of our function. And I'll go into more detail on how these nodes over here work in a minute. Also, the reason we are using the value 4 over here is because our pieces can only be rotated in 4 ways. Hence why we have 4 execution pins over here. So back in our event graph, I have my rotate function in our for loops for rendering our Tetromino pieces, and I'm using the output of the rotated index to choose a character from our character array over here. Now we are going to run this project, and you can see our piece is actually rotating. So to understand how we are rotating our pieces, I'm going to be using this diagram over here. So these are the indexes of our piece starting from 0 and ending at 15. We can find the index of any cell in here by using the same equation we already used several times, the y into field width plus x. We will use this equation to rotate our piece to 0 degrees, which is also the rotation it would have by default. However, if I want my piece rotated to 90 degrees over here, then the indexes of our piece would look like this, and our formula for finding out the piece would also have to change to y plus 12 minus x into 4. So suppose I wanted to know the index of this cell over here. By using the formula, you would get the value 5. And the way we come up with these formulas is really similar to a mathematical concept called arithmetic sequences. So you can check it out if you want to learn more. So back over here, if our piece was now rotated to 180 degrees instead, our indexes would look like this, and our formula would also change to 15 minus y into 4 minus x. And finally at 270 degrees, our formula for finding out the index would be 3 minus y plus x into 4. Now there is something you need to be aware of with the way we rotate our pieces. And to better explain what it is, I'm going to run this game. And you can't really see what the issue is with this particular piece as I rotate it. But if I were to use another piece, you can see our piece is jumping around when we rotate it. And the reason for that is because our pieces are rotated as this 4x4 square. If the x's aren't properly placed, it appears like it's jumping around when we rotate it. So yeah, that's it for this video. In the next part of our tutorial, we're going to add collision to our pieces so it does not go out of boundaries like this. And we will also add the logic needed to make our pieces move down the playfield every tick and more. Like and subscribe if you liked the video, and if you want to see more content from me, I would really appreciate your support on Patreon. Thanks a lot for watching and see you later. Bye.